Gary Landreth.
Good morning. So I'm Gary Landreth. I'm a professor of neurosciences at Case Western Reserve University, and I'm here representing the CART Fund, which the acronym is for Coins Against Alzheimer's Research Trust, which originated in the Rotary clubs in South Carolina. This is a fantastic program, which I understand has been adopted here. I'd like to give you one example of how I think your monies have been used productively. So, oh, okay, I got it. Ah, there. So, okay, excellent. Okay, so it's been 100 years since Alois Alzheimer's described the first case of Alzheimer's disease. He saw a 51-year-old woman who exhibited profound memory loss and a range of abnormal behaviors. When she died, he took her brain and looked through it and found what we now recognize as the canonical hallmarks of Alzheimer's disease, which are neurofibrillary tangles and amyloid plaques. I think it's important to recognize that until recently, this was considered a rare disease. And if I could just have a show of hands, how many people in this room have been touched in one way or the other by Alzheimer's disease? So it's virtually everyone in the room. This is the disease of the 21st century. Next slide. So again, I probably don't have to tell this group. So Alzheimer's disease is characterized by the dysfunction of higher information processing and recall. It is what characterizes us as human beings. It is the most common form of dementia. There are many varieties of dementia. Alzheimer's comprises about 85% of all dementias. It is the largest unmet need in medicine. Next slide. So what are the symptoms? Well, the reason most people show up in their doctor's offices is because they lose their capacity to form short-term memories. Long-term memories persist generally until late in the disease. What this really means is that you're forgetting your car keys, you forget where you are, and so the characteristic features of these are the inability to use language effectively. Spatial perception, it's well known that Alzheimer's patients get lost because they can't navigate in space any longer. Then there's a range of functions which we call executive functions, but what we really mean is that these individuals lose their capacity to have good judgment and they can't accurately problem solve anymore. As the disease progresses, there's a panorama of behavioral changes, the inability to pay attention. Depression is very common, particularly in the early stages of the disease. Aggression in individuals who didn't show any signs of this in their earlier lives, and apathy. Next slide, please. This is the disease of the 21st century. There are 5.3 million Americans with Alzheimer's disease today. It is an epidemic because that number will rise to 16 million individuals in the United States by 2050. We can fill every hospital bed in America with an Alzheimer's patient by the middle of the next this century. Next slide. Now, the reason why is that age is the largest risk factor for getting Alzheimer's disease. Through the wonders of modern medicine, we are living longer. And as that demographic changes, we're living long enough to get our Alzheimer's disease. About 2 or 3% of individuals at age 65 have Alzheimer's disease, but that number dramatically increases as a function of time. And the most important factoid on this slide is that roughly half of all individuals over the age of 85 have Alzheimer's disease. So let's think about that. That's a phenomenal number. And it is that age group, that demographic above the age of 85, which is the most rapidly increasing demographic in the country. This is a sobering statistic. Next slide. The cost of this disease is dramatic. Last year, it cost $200 billion to treat Alzheimer's disease. This is largely due to two reasons. One is on average 8 years from the time of diagnosis to the time of death. So this disease lasts a long time. At the end of the disease, most of these individuals are in custodial care, institutionalized care, and if any of you have had any experience with this, you know this is extraordinarily expensive. Overall, it costs about $20,000 to $40,000 per patient per year to treat this disease. It will cost $1.1 trillion by 2050 per year. The overall cumulative cost is $40 trillion, or $20 trillion. So, you know, we've had this discussion about the cost of health care in America. These numbers we're talking about now are going to pale into insignificance. This disease by itself has the capacity to break the American health care system. The most troubling fact out there is that we have no effective therapies for the disease. Now, I think those of you who've had experience that there are a variety of drugs which are prescribed for Alzheimer's patients. Aricept, Reminil, Cognex is one group. Memantine is another group. All these drugs do is they treat the symptoms of the disease, and they help a damaged nervous system work a little better for a little longer. For example, Aricept works in 1 in 5 patients for 6 to 9 months. It's highly prescribed because we have nothing else to offer, not because it's effective. Next slide. So, what causes Alzheimer's disease? Well, about 5% of Alzheimer's is genetic. That is, you inherit a mutation from your parents that confers the disease. It's rare. These people get their disease rather earlier in life, and it goes pretty fast. So the difficulty is that the other 95%, which is termed sporadic or late onset disease, we don't have any good idea for why these people get the disease, although I will have something to say about that. I think this is a shocking statistic. Now, the reason why individuals show cognitive deficits and memory deficits is because they're losing neurons in their brain. Now, neurons are the cells in the brain which communicate with each other and which subserve all the functions of our nervous system. It is important to recognize that those areas of the brain which are preferentially affected are indeed these areas associated with memory and language, which are the first symptoms of the disease. But in advanced cases, there is profound loss of the neurons in the brain, as evidenced by the shrunken brain in this late-stage Alzheimer's disease patient. Next slide. So, what Alzheimer described in 1907 was the classic pathology of the disease, which is typified by the deposition of what have been termed amyloid plaques. Now, these are just waxy, insoluble deposits that appear in the brain, and which are the earliest signs of Alzheimer's disease. Subsequently, the neurons show what we call neurofibrillary tangles, which what that means is that these are cells that are in the process of dying, and they have disordered cytoskeletons, which are called neurofibrillary tangles. The earliest feature of the disease is the failure of these neurons to effectively communicate, that is, to transmit information between each other. This is called synaptic failure. Eventually, these neurons die, and this is, represents it's an interesting problem because even at this late stage, we do not really understand why the neurons die, and that's a central piece of information which we completely don't understand. Next slide. So, as we look through the brains of Alzheimer's patients in late-stage disease, up to 30% of the parenchyma of the brain can be occupied by these amyloid plaques. These plaques are made up of a compound called amyloid beta, or beta amyloid. Next slide. And is entirely diagnostic for the disease. Through the wonders of modern imaging, and you may have heard about this summer, there's been an FDA-approved agent called Amyvid, which allows us to image in living human beings amyloid deposition in the brain. And through the use of these new technologies, we can examine basically your brain to see whether you have the earliest stages of the disease, which is amyloid deposition. And what you can see on this slide is that the dyes are injected, you put you into a PET scanner, and what we can see is, shown in red here, is the deposition of amyloid in an Alzheimer brain. Next slide. The important piece of this is what this is allowed to do is to make a rather remarkable discovery, is that the earliest signs of the disease, that is amyloid deposition, begins 10 to 15 years before these people show up in the doctor's office for memory problems. Now, this may be the most important slide I show you today, because what it says is as we think about therapy and preventing disease, we have to move back a decade or so. And when we think about treating this disease, this is a fundamental shift in our understanding about how to go about this disease. I don't know whether you saw the New York Times on Thursday this week. The FDA has just changed the rules whereby we will now be able to treat people who are cognitively normal but who have signs of amyloid deposition. This was previously not possible until this week. The other feature of this slide, which I think is important to recognize, is that there have been 28 failed clinical trials for Alzheimer's disease. And that's a stunning statistic. Most recently, there were 3 big trials that failed this summer. Now, if you look at this graph, we've been treating these people with these new drugs over onto the far right-hand side where they have dementia. So it's now evident that we were treating people who may not be susceptible to treatment because their disease is too advanced. So that's an extremely important reorientation of how we think about going about developing new therapies. Next slide. Now, those of us in the business thought that the reason why we got our Alzheimer's disease is because we made too much amyloid. Now, as you're listening to me, we're all producing prodigious amounts of amyloid as a normal consequence of electrical activity in the brain. And so we thought Alzheimer's people just made too much of it. It turns out that's not true. We're all making amyloid at pretty much the same rate. The problem is, in the Alzheimer's patients, they can't get rid of it. They can't clear it. And this also represents a fundamental change in how we think about this. This is just a quote from an article in the New York Times, which says just exactly what I said. It turns out people with Alzheimer's seem to make perfectly normal amounts of amyloid. They just can't get rid of it. It's like an overflowing sink caused by a clogged drain instead of a faucet that does not turn off. This changes everything. Next slide. So, now, while you're all sitting here listening to me, we're producing what are termed soluble forms of amyloid. These are little bitty pieces of amyloid. And normally, in a normal brain, these can be cut up and cleared into the peripheral circulation, and we can all go about our lives and have good memories and healthy brains. Next slide. Now, the difficulty is that there are age-related impairments in the clearance mechanisms. So I think we all know this. So some of us have our hair, some of us don't. Some of us, joints are good, some aren't good. Some of us can hear, some of us can't. And these biological functions deteriorate differently in each of us. So that's an individual variability. Same thing in the brain. In the processes that are responsible for clearing amyloid, decay in some people faster than others. And when that happens, next slide. This amyloid accumulates in the brain, and what that does is it poisons the capacity of one neuron to talk to the other, and this is what subserves the cognitive deficits we see in the disease. Next slide. As this process proceeds, these amyloid molecules form fibrils, the fibrils form plaques, and it is the formation of plaques which is associated with the loss of neurons in the disease. Next slide. Now, our contribution to this discussion comes from the recognition that we figured out how the clearance works. And it's a protein called apolipoprotein E, and that's really not important. But what you need to think about, this is the garbage disposal. We've figured out how the brain normally gets rid of the amyloid. Next slide. So I had a very clever graduate student, Paige Kramer, who arrived in the lab. At the time, we recognized that if we could increase the size of the garbage disposal, increase the size of the clearance mechanisms, we'd stay smarter longer. So that was the idea. Remarkably, we knew how to do this. And we found, and this is completely serendipitous, a drug called bexarotene, whose function is to increase the amount of apolipoprotein E in the brain, that is, to increase the disposal function. The great thing is this is an FDA-approved drug, and it has a really great safety profile, which means that we can move rapidly to translate these basic science findings into clinical trials. Next slide. So the idea is we give the drug, the amount of apolipoprotein E in the brain increases, we enhance the clearance of amyloid from the brain. That's the concept. Next slide. Now, through the wonders of modern molecular genetics, we can make mice that get human Alzheimer's disease, because we can put the human genes that go awry in Alzheimer's disease into the mouse, and the mouse gets what appears in some ways to be Alzheimer's disease. They lose their capacity to think and remember, and they get amyloid plaques. Now these aren't perfect, but they're all we have at the moment. Next slide. So what Paige did was she took an Alzheimer mouse, and she put a probe into the mouse's brain to measure the amount of amyloid in the brain in real time. she found a rather remarkable thing. She gave this drug, and within 6 hours, the levels of amyloid in the brain began to fall. This had never been seen before, and it's a remarkable finding. Next slide. Furthermore, these mice had amyloid plaques shown here in red. Now, we, like everybody else, thought once you got an amyloid plaque, you had that plaque until the bitter end. That these were static structures once formed, they were plaques. What Paige did was she went back in and asked the question, does drug treatment alter plaque deposition in the brain? And she got a really stunning result. She could remove half the plaques in the brain within 72 hours. This changed everything because we didn't think it was possible that this could occur in principle. And she can do it basically in a mouse in 72 hours. Next slide. Okay, so that's great. But the only thing we really care about is, are these guys smarter? So we interrogated their memory and cognition through a large number of tests. But I think the one that's most accessible and understandable to a lay audience is this nesting behavior. Now, your garden variety mouse, if given a paper towel, will make a nest in the corner of the cage every time. This is what mice do. Now, if we take an old Alzheimer mouse, and these guys are about a year old, they have lost the capacity to remember how to make nests. And so what Paige did was a really interesting experiment. She gave these guys a drug. And what you can see in this graph here is that almost as fast as she could look, within 2 to 3 days, these guys were making nests again. Now, they weren't great nests, but they were nests nonetheless. All right, so let's think about this. What Paige was able to show is that we can intervene in mice. Let's be clear about this. These are mice. We can intervene in mice and reverse both the pathological features of the disease and the impairments in memory and cognition, basically in a small number of days. And I think that's why this paper got such attention. Next slide. Okay, so where are we? So we basically finished the proof of principle studies, and this was published in a paper which was supported in part by the CART Fund. And I'll tell you about that in just a second. Right now we're trying to figure out how much drug to give and when to give it, to optimize this in a mouse. The next step is to move this into humans, and I am delighted to tell you that we started a pilot clinical trial the first week in January of this year to determine whether this drug works in human beings, in the normal brain, human brain, as it does in normal mice. Next slide. So this trial is currently underway. We're using state-of-the-art and very expensive technology. We will know the answer to this by the summer, and that in itself is a really impressive feat, and which would not have been possible even 2 years ago. So we're using state-of-the-art technologies. We're going to move as fast as prudent and our resources allow to determine whether we can move this into phase 2 trials. I discovered 2 weeks ago that the Cleveland Clinic at the Lou Ruvo Center in Las Vegas has already initiated a phase 2 trial, and they are about to start enrolling patients in that trial. So I don't know whether you guys appreciate it, but we're moving at warp speed. It has been under a year since this finding was reported, and we're already into 2 clinical trials. And I think this is nothing but good news if mice are like humans. So I'd like to take just a few microseconds to tell you about the CART program. So this is an absolutely fantastic program run originally out of the South Carolina Rotary clubs. And I think the acronym comes from, it's Coins Against Alzheimer's Research Trust. So I think as you came to the meeting, you had to empty your pockets into a bucket, all your change. And this is a really important initiative. As the federal budget contracts for biomedical research, the philanthropy from you and from other organizations are increasingly important. This is a very well-run program. In the business, it's recognized as one of the premier sources of funding in terms of quality. They have a world-class review process. Only the best science gets funded. But the key piece here is they will fund high-risk science that the NIH will not support. And they paid for this study, and for which I'm very grateful. Thank you.